Imagine this tiny probe way, way out past Pluto into that deep, empty space. And then it feels just this tiny pull, the sun's gravity kind of whispering it back home.
That's such a great way to picture it.
And that's where we're starting today. Not zooming across the universe, but diving deep right here inside our own planet. Think about, say, the Rio Grande Gorge. Looks immense, right?
Absolutely massive when you're there.
But stack that against the whole Earth, its depth is just, well, it's tiny.
Yeah.
0.008% of the Earth's radius. Barely a scratch.
It really does put surface features in perspective. We see mountains, oceans, but there's this whole other world churning away underneath us.
Yeah.
So complex.
Exactly. And that's what this deep dive is all about. We're digging into a chapter from Earth, Portrait of a Planet, pulling out the really essential stuff, the core geology, the big processes, even some real-world spots to help picture it.
Think of it as your guided tour, maybe.
Yeah, your shortcut to understanding Earth from its spot in the solar system right down to the very center.
So if you've ever wondered, what makes Earth tick, this is definitely for you. We'll tackle some complex ideas, sure, but we'll aim for clarity, those aha moments, without drowning you in jargon.
Right. Let's dive in. We'll start way out in the solar system, then drop through the atmosphere, skim the surface, and then make the big descent into Earth's layers. Structure, composition, what's driving it all. Okay.
It's like a plan. So our imaginary probe starts out in interstellar space. And the thing to grasp is just how empty it is, like less than 1 atom per liter. Almost nothing.
A near-perfect vacuum?
Pretty much. Maybe a few atoms left over from the Big Bang, or cosmic rays, high-energy bits shot out from exploding stars.
Then incredibly far out, maybe 50,000 AU. And an AU is Earth-Sun distance, right?
That's the one. 50,000 times that distance. Out there, the probe starts feeling the sun's gravity. Just a whisper, but it's the first sign of home.
Okay, come closer.
Around 3,500 AU, it hits the Oort Cloud. Picture this huge spherical haze of icy stuff. Frozen water, CO2, methane, basically leftovers from when the solar system formed.
Or stuff that got flung out early on.
Yeah, exactly. And it's where a lot of the long-period comets come from, the ones with really big orbits.
Okay, then closer still.
Around 200 AU, you enter the heliosphere. This is more like a giant magnetic bubble. It's formed by the solar wind particles streaming constantly from the sun.
And Voyager 1 actually crossed the edge of that bubble.
It did. That crossing is sort of seen as the technical edge of our solar system's direct influence.
Right. Keep going.
Next up, between about 30 and 55 AU is the Kuiper Belt. This one's more like a flattened donut beyond Neptune, also full of icy objects.
And that's where the shorter period comets come from.
Many of them, yes. Pluto's out there, Eris, 2 dwarf planets. And all that ice, if you added it up, might have as much mass as Mars. It's significant.
Okay, now we're really getting closer. Interplanetary space, past Neptune, the last big planet.
And even out here, the density of atoms, it actually jumps up quite a bit compared to interstellar space, maybe 100,000 atoms per liter.
Still practically nothing to us, but crowded compared to deep space.
Relatively speaking, yes. Then you pass the ice giant Uranus, then the gas giants, Saturn and Jupiter. Massive planets.
And between Mars and Jupiter, the asteroid belt.
Right. Millions of smaller, rocky things orbiting there. Not a dense field like in the movies. It's very spread out.
Yeah.
Plus you have other groups, like the Trojans and Greeks, sharing Jupiter's orbit.
And finally, the inner solar system, the rocky ones.
The 4 terrestrial planets. Mars, our Earth, Venus, and Mercury. And seeing them from space, you really notice how different they look. Earth's especially, with the blue oceans, the clouds.
They're very distinct.
Absolutely. And maybe we should quickly distinguish comets and asteroids. They're both smaller bodies, but different.
Good point. Comets are icy.
Yeah, basically icy, dusty chunks, planetesimals. They have these long elliptical orbits. When they swing near the sun, the ice vaporizes, making the glowing head and tails we see.
Dirty snowballs, they call them.
That's the classic description. Short period ones from the Kuiper Belt, long period ones from the Oort Cloud way out there.
And there's that idea that comets might have brought water to early Earth. Maybe even life's ingredients.
It's a fascinating possibility, yeah. A cosmic delivery service.
Okay, so asteroids are the rocky ones.
Mostly rock and door metal, orbiting mainly in the asteroid belt. Some are leftover planetesimals that never grew bigger. Others are chunks from larger bodies that maybe had a core and mantle once, then got smashed up.
And they range in size.
Hugely. From dust specks up to Ceres, which is big enough to be round. A dwarf planet itself. It likely has rock and metal inside, with water ice around it. Most smaller ones are just irregular lumps.
But even altogether, they don't add up to much mass.
Surprisingly little, actually. Just a fraction of our moon's mass. So yeah, seeing Earth against all that really makes it stand out.
So the probe gets closer to Earth. What's the first thing it feels?
Our magnetic field. It's this invisible region of magnetic force surrounding the planet, like Earth is announcing itself.
And it's like a bar magnet inside, basically, with a north and south pole.
Fundamentally, yes, it's a dipole field. But here's a tricky bit. How physicists name poles versus how geographers do.
Ooh, how so?
Well, a physicist would say the magnetic pole near the geographic North Pole actually behaves like the south pole of a magnet because the north end of a compass needle points to it.
Ah, opposites attract. So it's technically a south magnetic pole up north.
Technically, yes. But to avoid endless confusion, geologists and geographers just call the magnetic pole near the geographic North Pole the North Magnetic Pole. It's simpler in practice.
Got it. Practicality wins. And this field isn't just sitting there, is it? It interacts with the solar wind.
Absolutely. That constant stream of charged particles from the sun pushes against our magnetic field, squashing it on the sun-facing side and stretching it out into a long teardrop shape on the night side.
And this whole structure is the magnetosphere.
Exactly. And it's crucial. It deflects most of those potentially harmful solar wind particles, acting like a shield.
A planetary force field.
Pretty much. But some particles get through.
And end up where?
They get trapped in the Van Allen belts. These are like two donut-shaped zones, thousands of kilometers up, filled with high-energy particles from the solar wind and cosmic rays. A second layer of defense.
Okay. But some particles still make it further down?
Yes, some spiral down along the magnetic field lines towards the poles. When they hit the atoms in our upper atmosphere, bang!
The auroras. Northern and southern lights.
That's them. The collisions energize the atmospheric gases, making them glow in those amazing displays.
Beautiful. Okay, so descending further, the probe finally enters the atmosphere itself.
Right, that envelope of gas surrounding the planet, even orbiting at 600 kilometers up, it's technically still in the very, very thin outer reaches. Takes about 96 minutes to go around.
And the air we breathe down here, it's mostly nitrogen.
About 78% nitrogen, yeah. Then 21% oxygen, which is vital for us. And then small amounts of other gases, argon, carbon dioxide, neon, methane, ozone, plus water vapor, which makes clouds.
And those clouds cover a lot of the planet.
Around 70% on average at any given time. It's interesting how different we are from Venus and Mars, whose atmospheres are mostly CO2.
Right. And as the probe descends, the air gets thicker, denser.
It does. Gravity pulls the air down, so the weight of the air above compresses the air below. Density increases as you get closer to the surface. At sea level, it's about 1.2 grams per liter.
And that creates pressure.
Atmospheric pressure, yeah.
Yeah.
The force of that air column pressing down. At sea level, we call it 1 atmosphere, or about 14.7 pounds per square inch.
Compare that to Mars.
Which has barely any atmosphere, maybe 0.006 times Earth's sea level pressure. And Venus.
Crushing.
Totally crushing, about 90 times Earth's pressure. Huge difference.
And pressure drops as you go up, like climbing a mountain.
Exactly. Top of Mount Everest, the pressure is only about a third of what it is at sea level. That's why climbers need oxygen and why planes need pressurized cabins. Humans really struggle above about 5.5 kilometers.
So most of the atmosphere is actually quite close to the ground.
Oh yeah, about 99% of it is below 50 kilometers altitude. Above 120 kilometers, it's incredibly thin. So even though gravity holds on to gas much further out, the bulk of the atmosphere is this relatively thin layer, and it's divided into layers based on temperature. That's right. We have the troposphere, where we live and where weather happens. Above that, the stratosphere, with the ozone layer. Then the mesosphere and the thermosphere way up high. The boundaries between them, tropopause, stratopause, are where the temperature trend reverses.
So vital for life, but still just a thin skin on the planet. Okay, probes orbiting, looking at the whole system. What are the big interacting parts?
Geologists call it the Earth system. You've got the atmosphere we just discussed, the hydrosphere, all the liquid water.
Oceans, lakes, rivers, groundwater.
Right. Then the cryosphere, the ice and snow. The biosphere, all these living things. And of course, the solid Earth itself. They're all linked, constantly exchanging energy and matter.
And Earth's location is key, right? The habitable zone.
Absolutely critical. It's that Goldilocks region around a star, where temperatures are just right for liquid water to exist on the surface. Not too hot, not too cold.
In our solar system, that's roughly between Venus and Mars.
Estimates vary, but roughly 0.8 to 2.5 AU, yeah. Earth is squarely in it. Mars is near the outer edge. Venus is too close, too hot.
And the atmosphere makes a big difference, too. Venus's thick CO2 traps heat. Mars' thin one doesn't.
Exactly. Location plus atmosphere equals surface conditions.
Okay, probe maps the surface, land and water.
Finds about 30% land, 70% surface water, mostly salty oceans, some fresh water, plus groundwater under the land and ice caps.
And the land isn't flat, it has topography.
Variations in elevation, yep. Plains, high mountains like Everest, deep valleys down to the Dead Sea shore, the lowest land point. You can see these features at different geotour sites.
Same for the ocean floor. It's not just flat mud.
Not at all. That's bathymetry. You have huge, flat abyssal plains, miles deep, but also massive mid-ocean ridges, underwater mountain ranges. The Mid-Atlantic Ridge is a prime example. You even see it popping up in Iceland.
Wow. And deep trenches, too.
Incredibly deep. The Mariana Trench goes down almost 11 kilometers. Just amazing features.
But even with Everest and the Mariana Trench, the overall variation is small compared to Earth's size.
Remarkably small. The total relief, highest point to lowest, is about 20 kilometers. Sounds like a lot, but it's only 0.3% of Earth's radius. Relatively speaking, Earth is smoother than a billiard ball.
That's incredible. So there's a way to show this distribution.
Yeah, the hypsometric curve. It plots how much of the Earth's surface is at different elevations or depths. It shows most land is fairly close to sea level, and most ocean floor is between 4 and 5 kilometers deep.
Which means small sea level changes can make a big difference to coastlines.
A very big difference, yeah.
Okay, robot landers touch down. What is the solid Earth actually made of elementally?
Well, out of all the natural elements, just 4 dominate. Iron, oxygen, silicon, and magnesium, they make up over 91% of the whole planet's mass.
Just 4 main ingredients, and they combine to make different materials.
Lots of different materials. You have organic chemicals, which are carbon-based, usually linked to life.
Then minerals.
Right. Solid natural substances where the atoms are arranged in an orderly pattern crystals. Most are inorganic.
What about glass?
Glass is solid too, but the atoms are jumbled, disordered, not crystalline.
And melts, like magma and lava.
Exactly. Liquid rock, magma below ground, lava once it erupts. You see old lava flows at lots of volcanic geotours.
And these combine to form rocks.
Rocks are basically solid aggregates, clumps of mineral crystals or grains, or sometimes natural glass. 3 main types depending on how they form.
Igneous.
Cooled from melt, sedimentary.
Cemented fragments or stuff precipitated from water.
You got it. And metamorphic.
Existing rocks changed by heat and pressure.
Perfect. Inside rocks, you have grains, individual crystals or fragments. If those grains are loose, not stuck together, that's sediment.
Like sand or gravel.
Exactly. Then you have metals, solids like iron or copper. They conduct electricity. You can shape them. Alloys or mixtures of metals. And finally, volatiles.
Things that easily turn into gas, like water.
Water, CO2, things like that. Stuff that's gas at surface conditions.
And most of Earth is made of silicate minerals, based on silicon and oxygen.
The vast majority, yes.
Yeah.
Silicon plus oxygen is the fundamental building block. So we talk about silicate rocks.
And we classify those based on how much silica they have.
Primarily the igneous ones, yeah. We look at the ratio of silica to iron and magnesium oxides. Felsic rocks have the most silica. They're less dense than granite, the stuff in countertops, or its fine-grained volcanic version, rhyolite.
Okay, then intermediate.
Like andesite or diorite, less silica than felsic.
Then mafica, denser.
Right. Less silica again, more iron and magnesium, denser. Basalt is the common fine-grained one, makes up ocean crust. Lava flows in Hawaii. Gabbro is the coarse-grained version.
And the least silica, most dense.
Ultramafic. Like peridotite, the main rock in the mantle. Comatite is a rare volcanic version. And the grain size fine versus coarse tells you if it cooled quickly, like lava, or slowly deep underground.
Got it. Now going deep inside the Earth, pressure and temperature.
They both skyrocket. The pressure comes from the sheer weight of all the rock piled on top. At the center, it's immense, maybe 3.6 million atmospheres.
Hard to even imagine.
It is. You see hint of it in deep mines. Engineers need serious supports because the rock wants to squeeze inwards under that pressure.
And the heat.
Also incredible. Miners know this even a few kilometers down. It gets really hot fast. That increase in temperature with depth is the geothermal gradient. In the upper crust, it averages maybe 15 to 30 degrees Celsius per kilometer down. It slows down deeper, but still, by 30-odd kilometers, you can be looking at 400 to 700 Celsius.
And at the core.
We can't measure it directly, obviously, but based on models and experiments, it's estimated to be over 4,700 degrees Celsius.
Wow, nearly as hot as the sun's surface, right beneath us.
Crazy to think about, isn't it?
So given we can't go there, how did we figure out the Earth even has these distinct layers? We can't just, drill down and look.
Exactly. That deepest hole ever drilled in Russia. It's just over 12 kilometers. It's like 0.2% of the way to the center. a tiny scratch.
So for the longest time, it was just imagination.
Pretty much. Ancient myths about underworlds, Hades. Later, people imagined giant caves, maybe filled with molten rock like in Jules Verne.
Journey to the center of the Earth.
That kind of thing. But science started getting clues, not from digging, but from weighing the Earth.
Okay, how does that work?
Well, we knew Earth's size, its volume, way back from Eratosthenes. Then, in the 1700s, Neville Maskelyne figured out a clever way to estimate its mass.
The plumb bob thing.
Yeah. He measured how much the gravity of a big mountain pulled a plumb bob slightly off vertical. From that, he could estimate the mountain's mass relative to Earth's and work out Earth's total mass.
That is clever. And that gave us density.
Right. Mass divided by volume. The average density came out around 5.5 grams per cubic centimeter. But surface rocks are much lighter, maybe 3 grams per cubic centimeter.
So the inside must be much denser, no huge empty caves.
Exactly. The logical conclusion was metal. Iron, maybe, which is dense. And because Earth is roughly spherical and spinning,
the dense stuff would have sunk to the middle?
had to. Otherwise, the spin would have flattened Earth out more. Plus, another clue came from tides.
How so?
The ocean tides are huge, meters high in places. But the land itself also rises and falls with the moon and sun's gravity, just much less than half a meter. That suggested most of the interior is solid, not a sloshing liquid ocean.
Right, it's stiff, so putting that together.
By the late 1800s, they had this basic picture. A light crust, like an eggshell, a denser, solid mantle, like the egg white, and a really dense metallic core, the yolk. But they didn't know how thick each layer was or exactly what it was made of.
Okay, so how did we get a sharper image?
Earthquakes. That was the key in the 20th century. When rocks break and slip along a fault, they release energy seismic waves that travel out through the Earth.
Like ripples from dropping a stone in water.
Sort of. But traveling through solid rock and along the surface, it's like snapping a stick. You feel the vibrations.
And we can detect these waves far away.
All over the world. There was this moment in 1889, a German scientist saw his sensitive pendulum wiggle after a big quake in Japan, show the energy went right through the planet.
And the insight was?
That these seismic waves travel at different speeds through different materials. Just like light bends going from air to water, seismic waves bend, reflect, and change speed when they cross boundaries between different rock types or densities inside the Earth.
So you can use the waves to map the inside, like ultrasound.
It's exactly like ultrasound. By tracking the arrival times of different types of seismic waves at seismographs around the world after an earthquake, scientists could start mapping out where these boundaries were and how deep. That revealed the detailed layered structure we know today.
And other rocky planets have this too. Crust, mantle, core.
Seems to be the basic pattern for terrestrial planets, yes.
Okay, so combining seismic data with other evidence, like meteorites.
Yes, meteorites are hugely important. Some are fragments of asteroids that melted and differentiated early on. They have iron cores and rocky mantles. Iron meteorites seem like samples of a core, stony meteorites, like samples of a mantle.
So they give us clues about Earth's bulk composition.
They do. Plus, studying rocks erupted from volcanoes, analyzing chunks of mantle rock sometimes carried up in magma, and doing lab experiments squeezing and heating minerals to see how they behave under deep Earth conditions. All these pieces together build the picture.
Right. Let's start at the top then. The crust.
Our home layer, chemically different from the mantle below. The boundary is called the MOHO, short for Mohorovicic discontinuity.
Named after the guy who found it using seismic waves.
That's the one. He noticed a sudden jump in seismic wave speed a few tens of kilometers down.
Yeah.
That's the base of the crust.
And its thickness varies a lot.
Dramatically.
Yeah.
Under the oceans, it's thin, maybe 7 to 10 kilometers. You could drive that far pretty quickly.
What's oceanic crust made of?
Typically a thin layer of mud and shells on top, then basalt, that fine-grained volcanic rock, and below that, gabbro, its coarser-grained equivalent. It's mafic in composition, rich in magnesium and iron. You can actually see old oceanic crust pushed up on land in places like Cyprus, a geotour site. Continental crust, under the continents, is much thicker, usually 25 to 70 kilometers.
Thinnest where it's stretching, thickest under mountains.
Exactly. Thinnest in rifts like East Africa. Thickest under the Himalayas where continents collide and crumple. It's much more varied than oceanic crust, all sorts of rock types, from mafic up to felsic like granite. Overall, it's less dense than oceanic crust.
And elementally, the crust is mostly oxygen and silicon.
By weight, yes. Oxygen is the most common atom by far because it's in silica and many other minerals.
Okay, beneath the MOHO, the mantle.
Huge layer. Goes down almost 2,900 kilometers, wraps around the core, and unlike the crust, It's pretty uniform in composition,
Made of.
almost entirely peridotite, that dark, dense, ultramafic rock. It's actually the most abundant rock type in the whole Earth by volume, even though we rarely see it at the surface. Sometimes bits get carried up by volcanoes.
And the mantle itself has layers or zones.
Yes, based on seismic wave speeds. There are jumps in velocity around 410 kilometers and 660 kilometers down. These aren't changes in rock type, but changes in the crystal structure of the peridotite minerals as pressure increases. So we talk about the upper mantle, the transition zone between those depths, and the lower mantle below 660 kilometers.
And is the mantle solid or liquid?
It's overwhelmingly solid. But below about 100 or 150 kilometers deep, it's so hot that it can flow very, very slowly, like incredibly thick tar or putty, maybe a few centimeters a year.
Plastic flow, not liquid melt.
Right. Though there might be tiny amounts of actual melt, like thin films between the solid grains in parts of the upper mantle.
And this slow flow is convection.
Yes.
Yeah.
Hotter, slightly less dense bits of mantle slowly rise. Cooler, denser bits slowly sink. It's like a giant, incredibly slow lava lamp circulation. And that's what drives plate tectonics at the surface.
Okay, quick detour. How does heat move around inside Earth generally?
3 main ways, plus one related one. There's radiation heat traveling as electromagnetic waves, like sunlight warming the Earth. Doesn't need a medium.
Okay.
Then conduction heat transfer by direct contact, atoms jiggling their neighbors, like heat moving along a metal poker in a fire. Works best in solids.
Got it.
Then convection heat transfer by the movement of a fluid, like hot water rising in a pot, carrying heat with it. This is key in the mantle and the outer core, driven by density differences.
And the fourth.
Advection. That's when heat is carried by a fluid moving through cracks or pores in a solid, like hot groundwater moving through rock, or magma rising and heating the crust around it.
Okay, thanks. Now back to layers. There's another way to slice it up, based on how it behaves. Lithosphere-asthenosphere.
Exactly. This isn't about chemistry. It's about mechanical strength, rigid versus plastic. The lithosphere is the rigid outer shell.
Includes the crust.
Yes, the crust plus the uppermost, coolest, rigid part of the mantle. All together, maybe 100 to 150 kilometers thick. This layer acts like a brittle plate. It breaks. Think cold wax.
Okay. And below that?
Is the asthenosphere. This is the part of the mantle that's hot enough to be plastic. It can flow slowly over long timescales without breaking. Think warm, soft wax. It's still mostly solid, but weaker than the lithosphere above it.
And the plates of the lithosphere move around on top of this softer asthenosphere.
That's the fundamental idea of plate tectonics, yes.
Is the boundary sharp?
Not really. It's more of a gradual transition. It happens where the mantle temperature hits about 1280 degrees Celsius, hot enough for peridotite to become ductile or flowable.
And lithosphere thickness varies too.
Yeah. Oceanic lithosphere tends to be thinner, maybe 100 kilometers. Continental lithosphere is generally thicker, 150 to 200 kilometers.
Okay, final destination. The core, right at the center. People once thought it might be gold.
Based on the high density, yeah, that was an early hopeful guess, but no.
So what is it?
It's mainly an iron alloy, over 80% iron plus nickel and smaller amounts of other elements like sulfur or oxygen perhaps. And seismic waves tell us it has 2 parts.
Outer and inner.
Right. The outer core is liquid. The temperature down there is incredibly high, so even though the pressure is huge, it's hot enough to melt the iron alloy.
And this liquid metal moving is important.
Crucial. The flow of this conductive liquid iron, stirred by Earth's rotation, acts like an electrical generator. That's what creates Earth's magnetic field, the geodynamo.
Wow. So the liquid outer core protects us via the magnetic field. What about the inner core?
The inner core, right at the very center, about 1,220 kilometers in radius, is solid.
Even though it's even hotter, maybe over 4,700 C.
Yes. Because the pressure is just so immense at the absolute center, it overcomes the temperature effect and forces the iron atoms into a solid crystal structure.
Incredible. Solid due to pressure.
And interestingly, the inner core is actually growing slowly. As the whole Earth gradually cools over billions of years, iron from the liquid outer core freezes onto the surface of the inner core.
It's growing. By how much?
Maybe about 1 millimeter per year. A tiny amount.
Yeah.
But over geological time, it adds up.
Wow. A living, growing heart to the planet. Okay, let's pull back then. What a journey. We went from the edge of the solar system right down to the Earth's growing inner core.
Yeah, we covered the layered structure, the material's crust, mantle, core, the processes like convection and heat flow, how we even know this stuff from seismic waves and other clues.
Key things for you listening to take away. Earth's special place in that habitable zone, how the magnetic field and atmosphere act as shields, the difference between the thin, brittle lithosphere and the flowing asthenosphere, and that contrast between the crust we live on and the vast mantle and core beneath.
And the dynamic nature of it all. It's not static. The mantle convects, the core generates the magnetic field, the inner core grows.
So here's something to think about. That growing inner core. As it gets bigger over millions, billions of years, how might that change the outer core, the magnetic field, maybe even processes nearer the surface? What does this journey make you wonder about Earth's past or its distant future?
It really drives home the scales involved, doesn't it? Deep time, immense pressures, slow but powerful changes, constantly reshaping our planet from the inside out.
Absolutely. And with that final thought, we have now worked our way through all the key parts of this chapter from Earth. Portrait of a planet, covering our place in space right down to the planet's deepest secrets.